What's up, Marauders? Video 3.6, Quantitative Information from Balanced Equations. The coefficients in a balanced equation, we've learned how to balance equations, can describe reactions in terms of how many molecules of reactants it takes to make each product, or you can also think about it in terms of moles of molecules. So we're going to do some stoichiometry in this section, and basically that is, given a certain amount of each reactant, determine how much product is going to be produced. So it's really useful, really common type of problem we're going to be seeing throughout the year in chemistry. Basically what you're going to be doing is you're going to be using conversion factors. So just like we did when we learned dimensional analysis, we're going to be multiplying by fractions. It's important to show all the units, make sure all the units cancel out. A couple of the conversion factors that we're going to be using, we're going to be using molar mass to convert from grams to moles, or later in the problem from moles back into grams. Remember, molar mass comes from the periodic table. And then we're going to be using the balanced equation and the mole ratio within the balanced equation. Let's look at some examples. Kind of the basic layout of most of these problems is we're typically going to be given the number of grams of a reactant, and we're going to be asked to find how many grams of a product can be produced. You can't convert directly from grams of reactant to grams of product. Okay, that's because in the balanced equation, it's not a gram ratio, it's a mole ratio. So most of these problems are going to be three steps. You're going to take the grams of reactant and using the molar mass of that substance, change it into moles. And then once you've turned it into moles, then you can use the molar ratio from the balanced equation to get moles of your product. And then you're going to take the moles of product and change that back into grams using molar mass. So most of these problems will be three steps. You can't take a shortcut and go from grams of reactant directly to grams of product because you need to have it in a mole ratio in your balanced equations. All right, so using that same strategy, let's try to solve this problem right here. When 10 grams of hydrogen are reacting with excess nitrogen, how many grams of ammonia are produced? So we've got a balanced equation right here, and we're interested in the ratio between hydrogen and ammonia. It says we have excess nitrogen. We don't need to worry about that. All we're interested in is the 3:2 ratio between the hydrogen and the ammonia that's being produced. So we're starting with 10 grams, and that's hydrogen. Hydrogen's diatomic, so it's H2, just like it shows in the equation. First step, we're going to take the grams and change that into moles using molar mass. So we're going to get the molar mass from the periodic table. Hydrogen's molar mass is 1, but it's H2, so we'll double it. So it's 2 grams of hydrogen for every 1 mole of hydrogen. Okay, we've got it so that the grams of hydrogen can cancel out. Next step is to use the mole ratio to go from moles of your reactant to moles of your product. All right, so we know moles of hydrogen need to go on the bottom. And moles of, what are we interested? Ammonia. So the ammonia is going to go on top. And then we look at the balanced equation to get this ratio. It tells us 2 moles of ammonia will be produced every time 3 moles of hydrogen react. So it's really important that you write in the units here, and that way you can see exactly what's canceling out and that you have the right thing on the top and the bottom of each fraction. Last step, we're going to take that from moles, go back into grams because we want our final answer to be in grams. So we're going to use a molar mass that comes from the periodic table. We're going to do moles of NH3 on the bottom, and we'll do grams of NH3 on the top. We can add up the molar mass of NH3, so we find nitrogen on the periodic table, it's 14, and then we have 3 hydrogens. Each hydrogen is 1, so the molar mass is 17 grams per mole. So 17 grams of ammonia for every 1 mole of ammonia. Okay, double check that we have everything set up right. Grams of hydrogen canceling out with grams of hydrogen. Moles of hydrogen canceling out with moles of hydrogen. Moles of ammonia, and then at the end we get grams of ammonia. So our units all cancel out. We do that one on our calculators, and we get 56.7 grams of ammonia. Next example, so we've got another balanced equation, different one this time. It says when 5 grams of oxygen react with excess hydrogen, how many grams of water can be produced? All right, so in this one, what are we starting with? 5 grams of oxygen. So we know first step of the problem, we're going to have grams of oxygen on the bottom. We're trying to go from grams into moles, so we'll put moles of oxygen on the top. This is the molar mass of oxygen, so we're going to look at the periodic table. When we look at the periodic table, oxygen has a molar mass of 16, right? But this is O2 in the equation, so we're going to do 16 times 2, or 32 grams for every mole of oxygen. Okay, important that you write the units in there so you make sure that you have the numbers in the right spot. I almost made a mistake. Next step, using the mole ratio to go from moles of oxygen, what we have, into moles of, we're interested in the water, so H2O. So moles of O2 go on the bottom, moles of H2O go on the top. And then we look at the ratio between these two things in the balanced equation, so we're getting 2 waters every time 1 oxygen reacts. And then last step, go from moles back into grams. So we're going to use the molar mass of water, so it's 2 times 1 for the hydrogens plus 16 for the oxygens, so it's 18 grams per mole. So we'll do 18 grams of H2O for every 1 mole of H2O. All right, check that everything is canceling out correctly. Grams of O2 cancels out. Moles of O2, moles of H2O, and then at the end we should get grams of H2O. When we do that in our calculator, remember you're multiplying everything that's on the top, dividing by everything that's on the bottom. It doesn't matter what order it's in. Some guys like to go 5 times 1 divided by 32 times 2 divided by 1 times 18 divided by 1, or you could do all the multiplication across the top first and then all divide by everything that's on the bottom. Doesn't make a difference. Either way, you're going to get 5.63 grams of H2O. All right, this one. So first thing we need to do in this one is, it looks like, write a balanced equation. So we'll get a little bit more practice with that. And then once we have that, we want to see when 20 grams of C8H18 octane are burned with excess oxygen, how many grams of water are produced? All right, so first thing is to balance this equation. So let's see, we've got 8 carbons, so we can try putting in 8 here. We have 18 hydrogens, so we would need to put a 9 here. And then that would give me, let's see, 8 times 2, 16 oxygens here, and then 9 more oxygens over here. So that's a total of 25 oxygens. That doesn't really balance. That would be 25 over 2. We don't really want to use fractions. So what we're going to do here is to double all the coefficients. So we'll put a 2 here. Then we're going to need to change this to a 16. We're going to need to make this an 18. And we'll make this 25. Okay, so that's kind of the process I would use when I'm balancing an equation like that. Now we have, let's see, 16 times 2, we've got 32 oxygens on this side, or from the carbon dioxide. We've got 18 from the water, and so that's a total of 50 on this side, and 25 times 2 is also 50, so our oxygens are balanced as well. All right, once we've got the equation balanced, then we're going to do our stoichiometry. So we're going to take our octane C8H18, change that from grams into moles. So we need to add up a molar mass for the octane. So we have 8 carbons. Each carbon has a mass of 12. And then we have 18 hydrogens, which each have a mass of 1. So when we do that, I think it gives us 114 grams per mole for the octane. All right, so let's see, the grams are on top, so they need to go on the bottom. Grams C8H18. And then we want to change it into moles. C8H18. Okay, units that you have go on the bottom, units that you want go on the top. So every mole of C8H18 from the molar mass from the periodic table is, we just added it up, 114 grams per mole. All right, next step, we want to go from what we have, moles of C8H18 H18, and we want to turn that into how many grams of water are being produced. We're interested in the water, so moles of H2O, and there's going to be carbon dioxide produced as well at the same time, but the question is not asking us about how much of that's going to be produced. So our ratio between the water and the octane is 18 for the water every time 2 octane are used. So 18 over 2. You could reduce that, but there's really no need to. I usually just leave it the same as what the coefficients are in the balanced equation. All right, and then next step is to go back into grams for the water. So we'll do grams of H2O on the top, moles of H2O on the bottom. Add up the molar mass of water. So it's 2 times 1 for the hydrogens plus 16 for the oxygen, so it's 18 grams per mole. So 18 grams of water for every 1 mole of water. And we do this on our calculators, and we get 28.4 grams of H2O. All right, one more example. It says zinc metal reacts with silver nitrate to produce silver metal and zinc nitrate. All right, so the first thing we need to do here is going to be to write a balanced equation. So it says zinc metal, so zinc metal, just Zn, and then plus silver nitrate. So I know silver ions have a +1 charge, nitrate, NO3 with a -1 charge, so AgNO3. Those are your reactants, and they're going to produce silver metal, so metals by themselves, just whatever the symbol for the metal is, and then zinc nitrate. So when zinc forms ions, they have a +2 charge, so to pair up with the nitrate, you're going to need to have ZnNO3 parentheses 2. You need to have 2 nitrates with each zinc because the charge of the zinc ion is +2. Over here, the charge of the silver ion is just +1. All right, so get all the formulas correct first. Then you can go back and balance it. When we go back and balance it, let's see, so we have 2 nitrates here, so you need a 2. That's 2 silvers, so we need 2 silvers on that side, and then it's balanced. All right, so now for the stoichiometry part, we're starting with 5 grams of silver, 5 grams of Ag. First step, go from grams to moles. So grams of silver go on the bottom. We look up the molar mass of silver on the periodic table. It's 107.9 grams of silver for every 1 mole of silver. All right, moles of silver on the bottom. Moles of, what are we interested in this problem? How many grams of zinc? So we're trying to find out about the zinc, so the zinc should go on top. Okay, look at the ratio between those two things. So the silver has a coefficient of 2 in front of it, and the zinc has a coefficient of 1 in front of it. So it's a 1-to-2 ratio between zinc that's going to be used and silver that's going to be produced. It doesn't really matter if these things are on the product or reactant side. You can, like in this question, it's asking how much of the reactant is needed to produce a certain amount of the product. Other questions, you start with the product and you're asked, or you start with the reactant and you're asked how much of the product is formed. It doesn't really make any difference. You just look at the ratio in the balanced equation. And if you write the units in each time, it's pretty simple. And so my last step in this problem is going to be to change the moles of zinc back into grams. So grams of zinc will be on the top because that's what I want. Moles of zinc will be on the bottom because that's what I have. And the molar mass of zinc from the periodic table, 65.4 grams for every 1 mole. Make sure everything cancels out. So we've got grams of silver, moles of zinc. Do that into our calculators and you get 1.51 grams of zinc.